minus 8 plus 10, that's 2. And then minus 8 plus 0 is minus 8. So V is this guy. Now, obviously, you understand that these are, at the same time, the coordinates of V in a canonical basis of R4. Well, that's obvious. It's minus 2 times 1, 0, 0, 0, plus, minus 4 times 0. Or you can write it if you wish, just for fun. So what we have as a vector is actually its representation in a canonical basis. Not a big deal. We don't need to write this ever in life, but just to make sure you know what's going on here. So my vector and its representation in canonical basis, that's the same thing. So you see this vector V, which is here, its coordinates in basis B2 are minus 2 and 5. Now I could ask, hey, but what are the coordinates of this guy in basis B1? Well, what do you need to do? Well, you need to solve the system X equal B, as we did before. So we are not going to repeat it for nothing. Let's say I give you coordinates of U in basis B2 again, and this time it is, let's say, 3 and minus 1 for some reason. So this means that U is equal to 3 times the first vector in the basis. That's why we call it ordered basis. And then minus 1 times the second vector. And all I need to do is compute. So I have 3, 6, so 12 minus 2 is 10, and then 12. So this is vector U. Its coordinates in basis B2 are 3 and minus 1. So you see clearly that coordinates have nothing to do with the components of the vector. So that's why we use this example, so you clearly see these things. Don't mix them. So all this was kind of easy because all I had to do in this case is just multiply these coefficients by the basis vectors, add this stuff up, and get my vector. So that's Sherlock Holmes, that's easy. The previous part was given basis, given a vector, find coordinates. That was more elaborate because you need to solve Ax equal B. Now, what would be fun is to go from one basis to another basis. What I mean by that is, I give you coordinates of a guy or a vector in basis B1, and I ask you, hey, what are the coordinates of the same vector in basis B2? And then you scratch your head, and you don't know. Well, one way of doing it would be this. I give you the coordinates, you compute the vector, and then you solve the system Ax equal B using the other basis. And then obviously I'm evil, and I'm going to ask you for another set of coordinates of another guy, and then you're going to do the same process again, and it's going to take time. And when you're done, I'm going to ask again for another guy, and you're going to do the same process, and at some point you can start hating me. So, in order for you to like me, I'm going to show you how to do all this automatically, quickly, in a smart way. So what we want now, as a third part, is to go from one basis to another. So, given the coordinates in one basis, what are the coordinates of the guy in another basis? Obviously, I need to give you both bases. So one way would be the long way that I just explained, and that's not really smart. And the smart way would be to actually build transition matrix, which is kind of dictionary. Instead of translating one word at a time, you have a tool that automatically translates every word from English to Spanish. Boom. So that would be fun, and that's our transition matrix. So this is N, I hope. always two bases of the same linear space. So we have a linear space, we have two bases for the linear space, and we would like to jump from one linear space to another, from coordinates in one basis to coordinates in another basis. So what do we do? The smart way would be to actually build this transition matrix. So what is the transition matrix? It's a square matrix that is invertible on top of that. That's beautiful. And the idea is actually to express basis vectors of B1 in terms of basis vectors of B2, which means you find their coordinates. So how do we do this? Here it is. So again, my basis B1 and B2, just to remind. So 1, 2, 3, 4, and 0, 0, 1, 0. So B2 was 1, 2, 4, 4, and 0, 0, 2, 0. So what I want is having the coordinates of a given vector in basis B1, I want to figure out what are the coordinates of the same vector in basis B2. But I want to do that a lot, and often for a lot of vectors. So I need to be smart a little bit. So the idea is express basis vectors from B1 in terms of coordinates of basis vectors of B2. So I'm going from B1 to B2. So I want to express this vector from B1 as a linear combination of vectors in B2. Then I want to express this vector from B1 as a linear combination of two vectors of B2. So how do I do that? Well, that's not complicated. Again, I need to solve a linear system. So do that. Solve. Now I'm going to be a little bit smarter than the previous time. I'm going to solve this system. So 1, 2, 3, 4. And also solve a system with the same matrix. So it's not really smart what I'm doing now. 0, 0, 1, 0. This is what I'm going to do. Find solution for these. So solution here will be x1, y1, and it's already computed somewhere. It's 1, negative 1 over 2. And solution here will be x2, y2. And somebody computed that also. It's 0, 1 over 2. So what this means is that the coordinates of this basis vector, so given by solution of this system, in basis B2 are 1 and negative 1 over 2. Coordinates of the second basis vector are given as a solution of this system and are 0 and negative 1 over 2. So the transition matrix is actually given by these two columns. And we write it clearly. So transition matrix T from B1 to B2. So it's clear from which coordinates to which we go, and first column is 1, negative 1 over 2, and the second column is 0, 1 over 2. That's it. That's my matrix going from B1 to B2, which means now I can give you coordinates of any guy in B1, and all you need to do is multiply it by this matrix, and you'll get coordinates in the basis B2. Yeah. So how does that work? Well, let's see. So vector V in basis B1, let's say coordinates are 2 and minus 2 for some reason. Well, I can find what is vector V, obviously, but all I want now is coordinates of the same vector in basis B2. So coordinates of vector V in basis B2. So what do? I use this transition matrix from B1 to B2, and I'm done. So coordinates of the vector basis B2 are just, so let me write schematically, B1 to B2, that's a matrix, times coordinates of V in B1. So that's schematic. In more concrete terms, I just copy the matrix and multiply by the coordinates of the guy in B1, which are these. And once I'm done, if I know how to compute, I'll get my coordinates in B2. So I have this time, this is 2, plus 0 is 2, beautiful. So this is minus 1 is minus 2, coordinates in B2. Cute? Then you go, hey man, but they're the same. Isn't that weird? Maybe. Let's try another one. If I give you a vector 2 and 7 in B1, what are its coordinates in B2? So the same transition matrix, all you do is change this, and then you have this, and then you have minus 1. So minus 1 plus 7 over 2. So 5 over 2. Cool. So those are the coordinates of the same guy in a different basis. So you can do this all day long. And then some smart guy will ask, yeah, but that's good. I'm going from coordinates in basis B1 into coordinates in basis B2. Nice. But what if you're evil to the point that you give me coordinates in basis B2 and then ask me to produce coordinates in basis B1? Should I start the process all over again? Well, that's an option. Or you can compute the inverse of this matrix. That will do the work. So just a note, the transition matrix from basis B2 to basis B1 is just the inverse of this one. So T B2 to B1 is actually the inverse of this guy. So I'm going to write it schematically. You put the brackets. So the inverse. So somebody computed the inverse, and the inverse is 2b1, the inverse is cubed is 1, 1, 0, 2. So this is going from b2 to b1. So if somebody gives you coordinates of a vector in b2, basis b2, to find the coordinates of the same vector in basis b1, all you need to do is multiply it by this matrix. Example, given, or change the name, u, basis b2, let's say it is -3 and 1. Find u in b1. This anymore. And you see your transition matrix is always square and is always invertible. Okay, so that's not complicated. So u in b1 is equal to this matrix, so the transition matrix from b2 to b1 times the coordinates of u in b2, which are given. So it's 1, 1, 0, 2 times the coordinates of -3, 1. Ta-da. So you have -3 plus 0. Then you have -3 plus 2 minus 1. So these are the coordinates of the guy in basis b1. If you want to know who's the guy, well, that's not complicated. It's -3 times the first basis vector of b1 minus 1 times the second basis vector of b1. But the same guy is actually equal to -3 times the first basis vector of b2 plus 1 times the second basis vector of b2. Well, that's not a big deal. It's the same guy, obviously. So that's the way you would proceed in order to find the transition matrix and to go from one set of coordinates to another. It's quite a straightforward procedure. Once you have your transition matrix, you're pretty much set. And one trick, not supposed to tell you, but let's say this will give you some edge. Let's say you need to find transition matrix from basis b1 to b2. Cool. You do it and then you realize that might be a long process. But for some reason, finding transition matrix from b2 to b1 is much easier. Well, guess what? You can do that and then take the inverse. So you get what you're asked for. So that's something you can use if you wish. Just for fun, I'm still wondering who's u. Who's the vector u? We said, well, u is -3 times the first vector of b1. Where is b1? No, b2. It's expressed in b2. So b2 was 1, 2, 4, 4. And it's plus 1 times the second vector of b2, which is 0, 0, 2, 0. So we compute this, and we get -3, then we get -6, then we get -12 plus 2 is -10, then we get -12. That's our guy. We were talking about this guy all the way. So now you wonder probably, is that the same as what we would get if we use these coordinates from b1? Well, let's see. I hope it is, because if it's not, somebody doesn't know what he's doing. 1, 2, 3, 4. So these are the basis vector of b1. -1 times 0, 0, 1, 0. So now your calculator's out. -3, -6, -9, -1 is -10. Good news. -12 here. Hey, the same guy. Surprised? No, it's supposed to be the same guy. It's the same puppy, just his name is expressed in two different languages. Come on. We knew that. Nothing new, man. So that's how you find the thing. Obviously, the process is a little bit longer if you have vectors with 3 components, but it's not a big deal again. Just one example quickly with 3 components, because by now we know what to do. So I'm going to R3, have 2 bases for R3, and then say find the transition matrix from basis B1 of R3 to basis B2 of R3. And you'll say that's not a big deal, because I know what to do. So R3 span of B1 and is equal to span of B2, and I'm going to define B1 and B2. Obviously these are bases with having vectors with 3 components. So B1 will be a canonical basis. That's cute. And B2 will be some a little bit more elaborated basis, just to have a suffer a bit, sweat from time to time. So 1 minus 1. Cool. So now what I want is to find transition matrices from basis B1 to B2, let's say, or from basis B2 to basis B1. Whichever one is easier. And then I find the inverse of the other. Or solve again, depends. It's the same thing. So if I want to find the transition matrix from B1 to B2, so find the transition matrix what do we do? Big deal, just solve the system. I need to express every single vector in a basis B1 as a linear combination of basis vectors in B2. How do I do that? Solve Gauss-Jordan, with A being the vectors from B2, and the B, the second right-hand side member, will be this one at the first, then second, and third, and then we solve. So what I need to do actually is to solve a big system. Because it's the same matrix. So simultaneously I'm solving all 3 equations because I'm a little bit smart. I don't want to work for nothing. So once I solve this, I'll get identity on this side here and transition matrix on this side. So apply Gauss-Jordan until you get identity 3 by 3 here, and transition matrix will be here. Cute. So once you do all this, the transition matrix from B1 to B2 is, well, I computed that, 1 over 2, negative 3 over 2, 1, 0, 1, 0, 1 over 4, 1 over 4, and negative 1 over 2. So this is the transition matrix from basis B1 to basis B2. Nice. So you need to do the process. Well, nothing special, we learned already how to do it. So now question, what's the transition matrix from basis B2 to basis B1? Well, it's obviously the inverse of this one. Yeah, who's going to compute the inverse of that one? Huh? Not me. We need to be a little bit smarter than that. So since we have B1 as canonical basis, this will simplify our life. So B transition matrix from B2 to B1 is equal to inverse of this. That's officially the case. There's nothing new there. And you can compute it and there's nothing wrong, just long. So it's the inverse of this. Well, I have good news for you. If you compute the inverse, you're going to get this guy here. This is because we are dealing with canonical basis as one of the bases. Life is a little bit simpler. So but in general, if I give you just two random bases of R3, well, you will need to compute the inverse or swap these two and then proceed again. So that's the way you do to find transition matrix. So now if I give you coordinates of a guy in basis B1, and I ask you what are the coordinates of the same guy in basis B2, well, not big deal. You multiply the coordinates by this matrix and you get it. So let's say we do just that. Given U in B1 is equal to 202, so in B1, find U in B2. Well, all I need is to multiply these coordinates by the transition matrix from B1 to B2. So the coordinates of the guy U in basis B2, just multiplication. So need to be able to multiply at some point. If not, you have your calculator, hopefully, able to calculate. So 202. So this goes from B1 to B2. And these are the coordinates in B1. And I'm going to get my coordinates in B2. So this 1 plus 0 plus 1/2, so 3/2. So this is minus 3 plus 0 plus 1/2, so 3.5, 7/2. And then you have 2 plus 0 minus 2, no, minus 1 is 1. This is what you get, and those are the coordinates of the same guy in basis, yeah, it's fine. In basis B2. All good. Simple. If you want to know who's the guy, well, you have two ways. Either you multiply these coefficients by the basis vectors of B2, or, if you're smart enough to realize that B1 was canonical basis, well, these are the coefficients in front of the canonical vectors, so the vector is actually 202. Something similar, if I give you, so given, let's say, Z in B2, so coordinates, let's say, -1, 2, and 3 in B2, find the coordinates of the same vector, Z, in basis B1. What do? Well, you need transition matrix from basis B2 to basis B1, and then multiply that matrix by these coordinates here, and you're done. Well, lucky for us, we have it here. So, coordinates of Z in B1 are given by, so I'm going to schematically write, I'm going from B2 to B1 times the coordinates of the guy in B2. So this will give me what I need. So this is the transition matrix. 1, 2, 1, and 1 times. So this is going from B2 to B1. And I'm taking my coordinates of Z in B2, which are given here. 1 is 1, 2, 3. And do all the get the result, which are the coordinates in basis B1. So let's do it. So -1 plus 2 is +1, and +3/2. So that's 1 plus 3/2 is 5/2 last time. And then this is -1 plus 0 plus 3, so that's +2. And then the last one, -2 plus 2, that's 0, -3. So these are the coordinates of our guy in basis B1. Now, knowing that basis B1 was canonical basis, well, I know also who's Z. Z is just this guy. So that's easy if you know what you're doing. Don't try to remember this by heart. It's totally useless and a waste of time. Don't do it. Understand what you're doing and it's going to be fine. Maybe a couple of problems for you just to suffer and have fun eventually. So I'm going to give you simple things in R2. So I'm going to give you 3 bases of R2 and then ask you to find transition matrices from one basis to another. So you'll have like 6 possibilities and then you'll have fun. Obviously, all you need is 3 and then compute the inverse. But if you don't know that, it's fine. You compute more. So this is just an exercise for you to go through the process. And once you do that, you're pretty much sure that you know how to find the transition matrix from one basis to another. So, for fun, it's all given bases B1, B2, B3 of R2. So what's B1? Oh, none of them is cute. So this will make you compute. B1, B2, value, 1, 2, 3, whoa, somebody was creative. So this is B3, 1, 3, 2, 3, whoa. Okay, so these are 3 bases of R2. Cool. So what I want now is transition matrix from one basis to another. So find the transition matrices. Transition matrix. So 1. So you go from B1 to B2, and then also you go from B2 to B1. All of these matrices will be 2 by 2 because you have 2 people in the basis. So obviously, once you find this guy is just the inverse, and you know how to compute the inverse of 2 by 2. That's long time done. So going from B1 to B3, and after that you go back. You go from B3, to B1. What do you do? Well, once you compute this, you compute the inverse and you get this guy, no trouble. And the last one, so go from B2 to B3. And once you do that, you can compute the inverse and go from B2, B3 to B2. Excited? So these things you can compute quite easily. The idea is to go through the process. Just apply the process slowly. There's nothing special in there. So that's it about change of basis, coordinates, and how to say puppy in several languages, and how to build a dictionary that will translate every other word, not just puppy, but cat and dog and donkey in different languages. So have fun, solve some problems, and I hope you'll do well in your exams also, as you should, I guess, after this good explanation. Have a good day, bye-bye.
Done?
I guess, but I didn't click on the thing.